Morning, campers. Mr. O'Sullivan here. Hey, we're going to continue talking about related rates problems. And the one we're going to do, the example for this problem set is the problem 2011. It was the Form B problem. And number 5, actually this problem, as you're asked to do 4 things. And the related rates problem is part D. We're going to go ahead, give a review of just kind of covering the other topics in A, B, and C. So let's go ahead and dive in. We're given a table, and the description is Ben rides a unicycle back and forth along a straight east-west track. The twice differentiable function B, and kind of underline that, highlight it. So if it's twice differentiable, we know that B prime also exists and B double prime also exists over our time interval that we're interested in. Also tells us that B and B prime are continuous. Models Ben's position on the track, measured in meters from the western end of the track at time t, measured in seconds from the start of the ride. Table above gives values for B at t and Ben's velocity v at t, measured in meters per second at selected times t. Part A asks us use the data in the table to approximate Ben's acceleration at time t equals 5 seconds, indicate units of measure. So we're going to have a unit point associated with part A. Part B says using correct units, interpret the meaning of the definite integral 0 to 60 of the absolute value of velocity dt in the context of this problem. Approximate that definite integral using a left Riemann sum with the subintervals indicated by the data in the table. Part C says for the closed interval from 40 to 60, must there be a time t when Ben's velocity is 2 meters per second. Justify your answer. And then part D, the related rates problem. A light is directly above the western end of the track. Ben rides so that at time t, the distance L at t between Ben and the light satisfies the equation L at t squared is equal to 12 squared plus B at t squared. At what rate is the distance between Ben and the light changing at time t equals 40? Okay, well, part A asks us to use the data in the table to approximate Ben's acceleration at time t equals 5 seconds. And we're also asked to indicate the units of measure. All right, well, we're going to approximate Ben's acceleration at t equals 5. So they're really asking us for to approximate the instantaneous rate of change of velocity, which would be acceleration at time 5. Now, in order for us to approximate it at time 5, the instantaneous rate of change, we're going to use the average rate of change for the times that are closest to 5. So 5, I'm looking at my times in my table here, and I have 0 and 10. So I'm going to use those. And I'm going to use the corresponding velocities at those times. So my approximation for the acceleration at time 5. So the approximation is going to be v at 10 minus v at 0 over 10 minus 0. Now I can't leave my answer like that because it's not numeric, so I just have to drop in v at 10 is 2.3 minus v at 0 is 2.0 over 10. And then I'm asked to use units of measure. Well, units for velocity are meters per second. So I would have meters per second. And I have to remember my units for time, which I have here in the denominator, would be seconds. So I'd have another second. So that would be meters per second squared. I'm just going to copy this down below. Ran out of room there. 2.3 is 2.0 over 10. And my units are meters per second squared. And that makes sense for units for acceleration. Okay. Part B, using correct units, interpret the meaning of the definite integral 0 to 60, absolute value of velocity with respect to time. You can also say that's the definite integral from 0 to 60 of speed. speed is the absolute value of velocity. So that, I just know that that is going to give me, so the first thing I want to say is that 0 to 60 via t, absolute value via t with respect to dt represents the total distance that Ben traveled. And here's where I want to throw in that distance is going to be in meters that Ben traveled in meters from time t equals 0 to t equals 60. So in that 60-second interval, that was the total distance, not the displacement, but the total distance that Ben traveled in meters over that time interval from time 0 to time 60. Okay, so that's the first part. Use correct units, and I interpreted that meaning. Now I'm going to approximate the definite integral using a left Riemann sum with subintervals indicated by the data in the table. Okay, so my approximation, I'm going to set up like this. 0, 60, integrand is speed, absolute value of velocity. Okay. Approximation, so I'm going to use the approximation symbol, not an equal sign. And then I'm just going to put it's a left Riemann sum. So I'm going to go to my table and I'm going to circle for each interval here. I'm going to have an interval. My time interval here from 0 to 10 is going to be 10. From 10 to 40, that's a difference of 30. And from 40 to 60, that's a difference of 20. So I'm going to have really 3 subintervals here. And then I want to make sure I'm picking up the right velocity. And so I want to circle for each interval. I want to circle like the velocity kind of on the left. So I'm going to use this one, and this one. Okay. And I notice it's absolute value of velocity. I'm looking at my velocity values though. All of them are positive. So I don't need to worry about taking a negative velocity value and making sure that I take the absolute value of that to make it positive. All of them are positive to start with. So now I'm just going to match this up. I'm going to take my interval of time for the first one. So 10 times the left velocity, 2.0. There's my first subinterval. Then lather, rinse, and repeat. 30 times 2.3 plus 20 times 2.5. I'm just going to leave my answer just like that. Don't need to simplify. Now the units that are going to go with that, if I think about this, my units for velocity are meters per second, and then my units for time, dt, would be seconds. So I'm multiplying meters per second times seconds, and so my units are going to be meters, and that makes sense because that would be a unit that I would have represent the total distance that was traveled. Okay. All right, so there's part B. Part C says for the interval, for the closed interval 40 to 60, must there be a time t when Ben's velocity is 2 meters per second? Justify your answer. Okay. Well, might be able to kind of recognize when they're asking us, must there be a time t? This is going to relate to a theorem. So it's a theorem question. Now, half our battle is going to be, okay, which theorem does this relate to? Is it intermediate value theorem? Is it mean value theorem for derivatives? Mean value theorem for integrals? Well, we could kind of look at it maybe a couple ways. We could say, all right, if it's intermediate value, I'm looking at, is velocity 2 meters per second in that interval from at between 40 and 60. So I could look at it. And again, if I'm looking at, I'm sorry, if it's intermediate value theorem, I'm just kind of checking that. IVT, I'm not sure. But if it is IVT, that would mean that if I look at the velocity at 40, so V at 40 from my table is 2.5. And then V at 60, velocity at 60, again for my table is 4.6. And so do I see is 2 in between that? Well, no. Okay, so I've kind of looked at it in terms of intermediate value theorem. It's not, doesn't fly according to the intermediate value theorem. But if I look at it in terms of the mean value theorem for derivatives, so MVT for derivatives, I got to check and see. In that case, that's going to be saying that now what I'm looking at is not the velocity at that interval, but I'm looking at the meters at those particular times. So I'm going to compare and say, all right, B at 40 minus B at 60 over 40 minus 60. What's that equal? So B at 40 is 9 minus B at 60 is 49. 40 minus 60. So that's going to be negative 40 over negative 20. That's equal to 2. And according to the mean value theorem for derivatives, that yes, there is going to be some point in that interval where Ben's velocity is equal to 2 meters per second. Because I basically just said, using the endpoints of my interval, the average rate of change of my position, which would be equal to my velocity, is equal to 2. So I've got that. So that checks. So I would say yes. And here I'm just going to restate kind of the problem back and just say yes, there must be a time t when Ben's velocity is 2 meters per second, according to the mean value theorem, MVT for derivatives. And I'm just going to add here as B at t is a twice differentiable function. So this is saying that I've met the 2 conditions necessary to invoke the mean value theorem for derivatives. All right. Okay, in part D, the related rates problem. So a light is directly above the western end of the track. Ben rides so that time t, the distance L at t between Ben and the light, satisfies the equation. At what rate is the distance between Ben and the light changing at time t equals 40? Okay, well, half the battle on this problem might be to draw a diagram. And so if I draw just a line that represents the track, and I'm just going to label this is the eastern end of the track, and this is the western end of the track. And then we've got a light. This is kind of a side view. We've got a light that's directly above the west end. That's my light. And then I've got Ben. Ben's on his unicycle. That's going to be a challenge. Okay, so there's a unicycle, there's that. That's the seat, and then Ben is sitting on that. Go, Ben, go. Okay, so Ben's riding his unicycle back and forth on his track. And we're saying the distance L at T between Ben and the light. Okay, so I'm going to kind of draw this, and we're going to say, all right, Ben, move my light just a little bit. So here's the light. Holy mackerel. So there's my light, and the distance between Ben and the light. And I'm going to draw that. Actually, I'm going to draw the distance between kind of the tire of the unicycle and the light. And we're calling that L at T. And then this distance from the end of the track to where Ben is, that's given by B at T. Okay, and they're telling us that this is really, it's the Pythagorean theorem, right? So I've got this right triangle here. So if L at T is my hypotenuse, if B at T is one of the legs of the right triangle, well, that must mean that the light is 12 feet above 12 feet, I guess, or it could be, looks like 12 meters. So that's going to be 12 meters above the track. Okay, so kind of got my diagram. Now I'm asked to find at what rate is the distance between Ben and the light changing at time 40. Okay, so again, related rates problem. We want to do a few things. We want to read the problem, then we want to convert kind of the words into calculus speak. And so looking at this, what we're asked to find, at what rate is the distance between Ben and the light changing? So really I'm looking right here for, I'm not looking for L at T because that's the distance, but I'm looking for the rate that the distance is changing at time 40. I'm really asked to find, that would be L prime. I'm really looking for L prime at 40. Okay. So that's big. Once I've kind of established that, now I can kind of work backwards and say, okay, how can I get L prime from this? Well, what I can do is I can take this geometric formula, the Pythagorean theorem, and the first thing I'm going to do is I'm going to take the derivative with respect to time. So I'm just going to recopy that right below. I got L at T squared is equal to 12 squared plus B at T squared. And again, that's given. That equation's given to me. So now I'm going to take the derivative with respect to time. And I'm going to have 2 L at T times L prime at T. Okay, so I got to remember the chain rule. So that can be a little tricky right here. Okay, so that's the left side of my equation. I'm doing D at T of the entire equation. And then I've got D at T of 12 squared. Well, it's a constant, so that's going to be 0. So then D at T of B at T squared is going to be, again, similar to what I had on the left side. It's going to be 2 B at T. So this is chain rule. That's the derivative of the outside function at the inside function times the derivative of the inside function, which is going to be B prime at T. Okay. Now I've got, okay, the good news is I'm looking for L prime at 40. So I've got L prime at T. That's good because that's the variable that I'm asked to find. Now I need to find, okay, is there a value for L at T, B at T, and B prime at T? Okay, well, B prime at T would be the change in the position, which is going to be the velocity. So really, v prime at t is equal to v at t. Okay, so I'm just going to recopy what I've got. Okay, now I've got a 2 on both sides of my equation. I can just, in essence, divide by 2. That goes away. And now I'm asked for when t equals 40. So I'm going to have L at 40 times L prime at 40 is equal to B at 40 times V at 40. And I'm going to solve for the variable I'm looking for. So I'm going to divide both sides by L at 40. L at 40 cancels, and so I have L prime at 40 is equal to this. Okay. So now, again, can't leave my answer there because it's not numeric. I have to kind of take care of the function notation. So B at 40, here's where I'm going to go back to my table. B at 40, here's 40. So B at 40 is 9. So that's B at 40. Actually, just going to write this. So B at 40 is 9. Okay, V at 40, my table is 2.5. Put that in parentheses so I don't get confused by that. Okay, and then L at 40. Okay, now here's what I have to do, just a little bit of work. I found that B at 40, B at 40 is equal to 9. And so L at 40, which is going to be the distance from the light directly to Ben, L at 40 by the Pythagorean theorem is going to be the square root of the square of the two legs at time 40. So that's going to be 12 squared plus 9 squared. So that is L at 40. Square root 12 squared plus 9 squared. Okay. So that is mine. I'm just going to rewrite that. That's L prime at 40. 9 times 2.5 over square root 12 squared plus 9 squared. And that represents the rate that the distance between Ben and the light is changing at time t equals 40. Now the units that would go with that, since that's the rate that the distance is changing, that's going to be meters per second. All right. Awesome. Okay, guys. Hope that was helpful. Have a good one.